Hi there, guys. Just before 9E, there was something which caught me off guard a little bit here. There was an extra formula which popped up, which isn't given in the formula booklet. And this is about the area of the object relating to the area of the image after a matrix transformation applied to that object. And it turns out that the area of the object, or what they're calling the pre-image here, when multiplied by the absolute value of the determinant of your matrix T, so your transformation matrix, is going to give you the area of the image, which is a pretty nice little formula. And there's an investigation which goes with this beforehand as well. But I think I'm going to show you this in a slightly different way. I'm going to verify it, not do a strict proof, but I'm going to verify it as simply as I can. Now, I tried doing the investigation here, and I have to say it takes quite a long time. And, you feel like you're just doing very easy things again and again. So, I'm going to try and make this a little simpler. And so this is what I've come up with in order to verify this formula here. Now, I've come up with 3 points over here. And so here are our 3 points. And if we make a triangle between these 3 points, then that triangle will have an area of a half. You can see that's going to be 1 times 1 divided by 2 is going to give you an area. Area in this case is going to be a half. Okay, that's area 1 if you like. Okay, so now, if we apply our matrix transformation, so this is any matrix transformation applying to those 3 coordinate points, 0, 0, 1, 0, and 0, 1, then you can see pretty straightforward that you're going to get this times this, which is nothing. Okay, and this times this, which is just going to give us the A, and this times this, which will just give us the B when we sum those 2 parts together. And this times this is, and sum together is 0. And then, of course, you're going to get C. And okay, so these here are our new points. So we've got 0, 0. Go on here, we've still got 0, 0 there. We've got AC, so that's our coordinate point. Let's put that over here. I don't know where these are exactly. These are just real numbers, A, B, C, and D. But let's just put it over there. And we've got BD, so we're coming up with our generic point BD over there as well. Okay, and what we want to do is connect the old area to the new area here. So the new area is going to be this area here. We're trying to connect these 2 areas together. So now we definitely know that this area is a half. And then we're thinking, well, what's the area of this thing here? Well, we can do that using the vector product. Now remember, if we've got the vector product, let's call this, say, for example, P, and let's call that Q. So the vector product will give us the area of the parallelogram. So if we do P times vector Q, and then we take the magnitude of that, that will give us the area of the parallelogram which it creates. So parallelogram would be this. So, Q followed by P and P followed by Q. So it would be that total parallelogram here. But if we just want the area of the triangle, then we're going to need to half that thing there, right? So, but normally when we do the vector product, we do it with 3 dimensions. So what I'm going to do with these vectors here, so P is going to be our vector A, C, and then 0. And then Q is going to be the vector B, D, and 0 as well. And we're going to need the magnitude of that. I'm going to put a half outside as well. Now, a lot of this is going to be super simple because when we do this times together, take away this times together for our first line of the vector product, that's just going to give us zeros. It's going to give us 0 there. And then when we do the second line, that's going to be this times this, and this times this being A and this being D here. So we're basically doing this times this, and this times this, but I see it as a kind of X which keeps sort of moving down to the next line. So we're doing 0 times by b, take away a times by 0, and obviously that's going to be 0 as well. Okay, so we're only going to get one line out of this in this column vector which is being created here. And so that's going to be our final line when we do this times this, take away this times this. So that's going to be, let's give myself a bit more room here. That's going to be AD, take away CB. Now that's our column vector there, but we still need the magnitude of that column vector. We need to half that as well. Now, you could use three-dimensional Pythagoras to work out the magnitude of that column vector, but quite simply, it has no magnitude in x or y. It only has z direction here. So that's the total size of the thing. So we can just say that this is equal to a half AD minus CB. Okay, so there's our final result. So this area here, this new area, this area, is going to be our half AD minus CB, and the original yellow area here, this was equal to an area of a half. Okay, so this is equal to our second area for our new object, or our image if you like. So that's the area of the second one. Just put that as a subscript. Okay, and you can see that the scale factor there is AD minus CB. Now, AD minus CB is the determinant, and obviously this could end up giving us a negative answer. And in terms of areas, there's no such thing as a negative area, so we're going to need to take the modulus of that thing. Okay, so, you know, for example, if you reflect this across the other side, then you might say, well, that's going to be enlarged by a negative scale factor, but that's still going to give us a positive area. Okay, so our scale factor is this, the magnitude of our determinant here, and you can see this is the expression for the determinant. Let's have a look at that. It's given to us here towards the end in AHL 1.14. Det A is given as AD minus BC. Now, you know, confusingly, they call the determinant of A this modulus of A, but we're now taking the modulus of A. So that's a little bit of confusing, but they're basically just saying, take the positive answer that's coming out there. Let's take the magnitude of the determinant of A. Okay, so I hope you agree that this has been shown to be true here. This is the multiplier from a half. On a half, we're multiplying by this, and that's this thing here. So I hope you agree that that's been shown to be true. Obviously, this isn't a proof, a strict proof, because we've taken a specific area here. So to come up with a proof here, we would need to take a generic area. Okay, so we'd need to come up with 3 generic points there, but algebraically, that's going to take a really long time to do, so that's why I've just done it like this. Okay, guys, well, thanks for that. Hopefully that makes some sense of it. I don't believe that that is given in the formula booklet. I don't see it anywhere. So given that this is discussed in the book, it pops up as a red squared rectangle. There you go, it's not given there. It's given here as well. The area of a parallelogram is given by the vector product, but nothing more than that. It's not there. So that's one of those little things which you're going to have to remember. Okay, so this thing here, something that you're going to need to remember. Okay, guys, well, thanks for listening, and again, good luck with the exercise.